To another edition of this learning distance adventure. We're going to talk a little bit about one of the more influential components in stoichiometry. Actually, it's a really good case of bringing everything together. We're going to talk a little bit about how to do the mass to mole to mole to mass, or some semblance thereof, and connect it to what we did a little bit earlier in the month with empirical formula and molecular formula. So let's get started. So what we're going to be doing is what's called a combustion analysis. Let's start by what's a combustion. You should know that a combustion is any reaction where you have some substance that contains carbon and hydrogen. It can contain other elements, but carbon and hydrogen are the two main elements in the compound. And we'll talk about what to do if there's other things in there besides just carbon and hydrogen, but we'll focus on carbon and hydrogen first. And it's burned, and two of the products, the two main products that are created, are going to be carbon dioxide and water. And we are going to, in Chem 1, focus on complete combustion, where all of the hydrocarbon becomes carbon dioxide and water. So I got two examples here. One's methane and one is butane, and both of which have the same style of reaction. We talked about these when we did reaction types. I think somebody actually in the chat had asked about the reaction type of combustion. And you've got this carbon hydrogen combination with some known value, some known ratio between the numbers, some empirical formula, and then having it react with molecules. But here's what I want you to notice, and here's the key part of a combustion analysis. All of the carbon from the hydrocarbon is turned into, or is reformed in the compound of carbon dioxide. And all of the hydrogen that is in the original compound is reformed into the water molecule. So if we're able to determine how many water molecules there are, we can figure out how many hydrogen atoms there are. And if we can figure out how many carbon dioxide molecules there are, then we can figure out how many carbon atoms there are, and then get a ratio that goes back to the original substance. And that's actually what we do for a combustion analysis. So a combustion analysis is one where you will control the combustion. And the way we talk about controlling the combustion is making sure there's sufficient oxygen. You have plenty of oxygen and excess of oxygen so that you don't run out. And all of the carbon dioxide, all of the carbon turns into carbon dioxide, and all of the hydrogen turns into water. And then you collect those two components. Now, we're not going to talk that much about how you collect those things, but they're usually referred to as things called scrubbers or desiccants. A desiccant is something that's going to absorb the water, and you'll see an increase in the mass of the desiccant. And a scrubber is a material that would, when the carbon dioxide goes through, it would trap the carbon dioxide, and then you could watch that material get heavier. And then knowing the mass of those two substances, you can determine the ratio of the carbon to hydrogen that you have, and that would be your empirical formula. So here's the steps that are associated with combustion analysis, and we're going to do these steps. So first thing you're going to do is you're going to be given a mass of carbon dioxide and giving a mass of water. And you're going to convert the mass of carbon dioxide over to moles of carbon dioxide. That will turn it into the molecule to molecule ratio. And then I know it's kind of a little bit redundant because there's one carbon in every one carbon dioxide, but then you're going to convert your carbon dioxide into moles of carbon. You can do the same thing with water. Take your mass of water, turn into moles of water using the molar mass of water. Convert your moles of water into moles of hydrogen, knowing that there's two hydrogens in every water. And then you're going to look at those numbers of moles of carbon and those numbers of moles of hydrogen, and determine the ratio or the empirical formula between the two substances. Let's look at a couple examples. So example number one says I have a 1.5 gram sample of some substance. It's a hydrocarbon, something that contains only carbon and hydrogen, and it undergoes complete combustion, meaning all of the oxygen you need is there, and you're going to create 4.41 grams of carbon dioxide and 2.70 grams of water. Then it asks the question is typical of this type of problem: what is the empirical formula? So first thing you want to do is, like I said, change your grams of carbon dioxide to moles of carbon dioxide by dividing by the molar mass. Looks like I put an extra decimal in there. I need to fix that. And then change your moles of carbon dioxide into moles of carbon again, it's a 1-to-1 ratio. So if you do this math right, and this one was set up to be pretty nice and clean, you turn out to get a 0.100 moles of carbon. You'll do the same thing for the water. You're going to take your grams of water and divide it by the molar mass of water. And then take your, that'll give you the moles of water. And then take the moles of water and convert it into moles of hydrogen. Now here, since H2O, there are 2 hydrogens in a water, you're going to have 2 moles of hydrogen for every 1 mole of water. And you're trying to do that math, you get 0.3. And without doing the crazy math of dividing by the smallest, you can definitely see that there's a 3-to-1 ratio here, which means the empirical formula for this substance that is burning in this Bunsen burner on the left-hand side has a formula of C1H3. So see how that wraps around to what we did before, where we're doing the same thing as trying to find those ratio of the atoms like we did before, but now we're getting it through stoichiometry. We're getting it from how many moles of carbon dioxide you have and how many moles of water do you have that you've collected as part of the reaction, and that goes back to your number of grams or moles of carbon and hydrogen. So the next way that you can make this process a little more complicated would be, as you see with the bold print here, what if I added an element? And a classic example is a lot of hydrocarbon compounds also contain oxygen. So if I have this example of a 0.25 gram sample, it contains carbon, hydrogen, and oxygen. Now, some of the oxygen that lands up in carbon dioxide and some of the oxygen that lands up in water also came from the substance, and some of it came from the oxygen you added. So it becomes a little more complicated how you do this. But you're still going to do the same thing. You're going to collect sample. So in this case, it collected 0.366 grams of carbon dioxide and 0.1500 grams of water. And I want to know what's the empirical formula. The process is very, very similar, but we have to worry about how to get that oxygen number. So here's what you do. So the process is very the same. What I've done is I've bolded the new steps. So you've changed your carbon dioxide, mass of carbon dioxide to moles. You change your moles of carbon dioxide to moles of carbon. And then, here's the tricky part. You're going to go back and take those moles of carbon and change them back to mass. Now, the reason for that is that would tell you how much of that total mass that you started with was carbon. You're going to do the same idea with water, change the mass of water to moles of water, moles of water to moles of hydrogen, and then change your moles of hydrogen over to mass of hydrogen, not H2, mass of hydrogen, H. And again, same logic there is, now I know the mass of the carbon and the mass of the hydrogen that was in my original sample, and I can figure out how many grams of oxygen there are, because the last thing you do is figure out how many grams of oxygen you have by saying, what's my total minus my mass of carbon minus my mass of hydrogen. That will give me the mass of oxygen, and then I convert that mass into moles. Why is that important? Well, now I have the moles of carbon, the moles of hydrogen, and the moles of oxygen, and I'm going to compare those 3 numbers just like I did before and try to get an empirical formula that will include the carbon, hydrogen, and now the oxygen, which I had to get a little backdoor, had to go around the corner and steal that by a little mass conversion. Let's see that problem that I had on the previous slide in order. So I have a 0.25 gram sample. I have 0.364 grams of carbon dioxide and 0.15 grams of water. So I'm going to do the same thing I've always done for the examples. Take my mass of carbon dioxide, divide it by the moles, so divided by the molar mass of carbon dioxide, and then 1-to-1 ratio, and I find the moles of carbon. Then I'm going to do the same thing for the water, just like the previous example. Take the grams of water divided by the molar mass of water times the 2-to-1 ratio, and I get the moles of hydrogen. Now that's 2 of them. Now I got to worry about that oxygen. Now what I'm going to do is going to take my moles of carbon that I got in the first step, multiply times the molar mass of carbon, the atom, and I'm going to find out that I have 0.1 grams of carbon. I'm going to take my moles of hydrogen in my second step, multiply times the molar mass of hydrogen, the atomic mass of hydrogen of 1.00794, and I get the 0.01678 grams of hydrogen. Then finally, I'm going to find out what my number of grams of oxygen are by subtracting from that 0.25 grams started with, subtract the 0.1 and subtract the 0.0168, and I find that I have 0.1332 grams of oxygen. And I need to change that to moles. So now what do I have? I have a number of moles of carbon, a number of moles of hydrogen, and a number of moles of oxygen. So I have those three values. I need to compare them just like I would for a typical empirical formula. So there's my moles of each one of them. Remember how you compare them if it's not obvious is you divide by the smallest. In this case, it's the 0.008325. I'm going to divide all of them by 0.008325, and lo and behold, I get a 1 to 2 to 1 ratio. So my empirical formula in this compound happens to be C1H2O1. This compound, whatever it was, has an empirical formula of C1H2O1. And there's a litany, a whole multitude of possible compounds that could be C1H2O1, C2H4O2, C3H6O6, and you see there's a lot of different molecular compounds that could meet that goal of that empirical compound. Well, for the last question that I have on this example is we're gonna take it that one step further, much like we did when we did our empirical formula and molecular formula combination. We're going to look at it and say, well, now what do I do with that information in order to find the molecular formula? So here is the last example on this slide or in this presentation. I want to know how to get the molecular formula from a combustion analysis, much like we did when we were doing the molecular formula, empirical formulas in the original section of this class. The thing we need in order to make that happen is we need a molar mass, and they gave it to us. At the end of this problem, they said that the molar mass or the molecular weight of this compound is approximately 108 grams per mole. So quinone, which is used in the dye industry and in photography, organic compound contains carbon, hydrogen, and oxygen, very much like our last example. I want to know what's the empirical formula of the compound. If I find that I need 0.105 grams of the compound, and when it completely combusts, I get 0.257 grams of carbon dioxide and 0.035750 grams of water. Then I want to know what's the molecular formula, because now I'm going to be given the mass, and I'm going to go from empirical formula like we did before to molecular formula. So let's see how this works. So you're going to do the same series of steps. You're going to see an extreme similarity because all the things are the same. And you're actually going to see my same mistake show up twice, I'm sure. There it is. There's that double dot. So I got 0.257 grams of carbon dioxide divided by the molar mass of carbon dioxide times the 1-to-1 ratio, since there's one carbon in one carbon dioxide. And I get that I have 0.00584 grams of carbon. I do the same thing for my water. I have the 0.0350 grams of water divided by the molar mass of water times the 2-to-1 ratio, since there are two hydrogens in a water, two hydrogens in an H2O, and I get the number of moles of hydrogen. I got to worry about that oxygen now. So I'm going to take my moles of carbon, converted into grams, my moles of hydrogen converted into grams, by, in each case, multiplying times the atomic mass of carbon and the atomic mass of hydrogen, and find what the total grams of oxygen was by subtracting the grams of carbon and the grams of hydrogen from the grams of total. And I get 0.031. So I figure out the number of moles, and I did, in this example, took a little liberties with sig figs, to be honest. So if that might bother you a little bit, I apologize. Is the fact that all my numbers of my moles were I had 3 digits past the decimal, except for my carbon, my oxygen would have. And if I rounded this, I was going to truncate off like 40% of that last number. So I left it there because I know that what I'm going to still be doing with this number is I'm still going to be doing some multiplication and division. So I'm going to go ahead and just keep it going and then look at it at the end, because we're looking at whole number ratios. So I left them there intentionally. So if that bothers anybody, I apologize. So I have the moles of carbon, the moles of hydrogen, and the moles of oxygen, and those things do not look anything like one another. So what I need to do is I need to take my 3 sets of moles. And again, what do you do when you have moles of 3 different elements in a compound and are determining the empirical formula? You divide by the smallest, which is the moles of oxygen. So I divide by the 0.09 0.00194. And lo and behold, it comes out to be really, really close to 3 to 2 to 1. So the empirical formula is C3H2O1. Those numbers are really close. You can do that with a calculator. It was like 2.997, and then I think it was actually 2.004, something like that. It's really, really close. Okay, so I get a 3 to 2 to 1 ratio. That's my empirical formula. That's only half the question. The other half of the question we asked for the molecular formula. Well, we've done this before, whereas if we know the empirical formula and we get the molar mass of the empirical formula, we can compare the molar mass of the empirical formula to the molar mass of the compound that was given to us, which was 108. Well, I can see this, but I'm going to do it anyway. If I take my 108 and divide it by 54, I get really, really close to 2. That means what I need to do to get the molecular formula is multiply all of my subscripts, my coefficients, not necessarily coefficients, my subscripts in my compound by the number 2. So the molecular formula turns out to be C6H4O2. So what we've done here is 3, and there's more. When you come to AP, we'll mess with this a little bit. AP. When you come to Chem 2, we'll mess with this a little bit more. But this is how you handle a compound that has only hydrogen and carbon, a compound that has hydrogen, carbon, and oxygen, and maybe even a compound that contains any other combinations of the two. But also we have a molecular formula. It's a nice blending of what we've done for the last few weeks since the beginning part of stoichiometry. So your homework for this is going to be a combustion analysis handout on OneNote. I hope, much like the last homeworks, I hope that I'll get that on there and downloaded while all the processing of these videos takes place. It normally takes about a solid hour between the two processes of editing and exporting these PowerPoints. I hope everybody's having a great day. It looks like it's going to be a little bit of a weird day, blah day. It's cooled up quite a bit here. I don't know about you guys when you're watching this, whether it be cool, rainy, or whatever. At the time of this, it is at 10 o'clock in the morning on Monday. So I hope everybody's safe, healthy, practicing that social distancing. And we're about less than a month away from the end of the school year, so we should be wrapping up Chemistry 1 really, really soon. I appreciate all your patience in this distance learning adventure. Take care. Have a great day. I'll see you on the next one. Toodles.